enough. Okay. Now let's move on the last part of this afternoon session. The first talk is from Mark Newman from University of Michigan, and he will talk about, it's not the same title.
Thank you. This is a totally different title from the one in your book. This talk was moved into this session from another session, and so I thought that I would talk about something different that suits this session better. So I'm going to say some fairly simple observations about the connection between graph spectra and phase transitions in networks. So I'm going to be talking about undirected networks. You can take a network, you can write down its adjacency matrix, which is a symmetric matrix for the undirected case. Every edge corresponds to 2 ones in the adjacency matrix, and then I can calculate its spectrum, its eigenvalues, and here I've done that for a small network. This network here is a famous network from the sociological literature. Some of you may recognize it. Here's its spectrum that I calculated, and what you see here is typical of what you see in many networks, that there's a bunch of closely spaced eigenvalues, and then there's a few outliers at the top. And the dividing line between what we call the band, the closely spaced bit, at the bottom, and the outliers at the top is kind of blurry for real networks like this, but it can be made sharp for certain model networks. There really is a continuous band of eigenvalues, and there are some outliers. Now, as a physicist, I like to think of this by analogy with physical systems, particularly quantum systems. It's only a sort of loose analogy, but I find it a useful one. I think you can think of the eigenvalues as being like the energy levels of a quantum system, and except that it's sort of upside down. The highest lying eigenvalues are playing the role of the ground state and the first few excited states in the quantum system. And then there's this sort of conduction band-like thing here. And what we'll see, what I'll talk about, is that basically, so this gives a nice separation between the structure and randomness in the network. That basically all the structure is contained in these high-lying states, and all the randomness is separated off from them in the band, and this is essentially why spectral methods are useful. So, so the basic idea I want to talk about today is it's about phase transitions, structural phase transitions in networks, and sort of to give away the punchline before I start, in quantum mechanical systems, it's well known that when energy levels cross over, you get quantum phase transitions. So these are zero temperature phase transitions, not the thermal kind that's due to thermal fluctuations, but quantum phase transitions that are due to quantum fluctuations, things like metal insulated transitions and stuff like that, occur when energy levels cross over, and there is a corresponding behavior in networks as well, where when energy levels cross over, you see phase transitions. This is not a new idea. This is a well-known concept in random matrix theory, but I feel like it hasn't been very thoroughly explored in the context of structural phase transitions in networks. So to start off with, let me give you a couple just very simple examples of why one might be interested in the spectra of networks, and then let me show you some of the transitions that I'm talking about. Here's a very simple example. Centrality is any measure in networks that gives a score to every node of the network in some effort to say which are the most influential or important nodes in the network. The ones that get the highest score are allegedly the most important ones. There are, of course, many different interpretations of what you might mean by influential in a network, and there are correspondingly many different definitions of centrality measures in networks. Perhaps the simplest one is just degree. How many connections does a node have? If I'm thinking of a friendship network, it's how many friends I have, and arguably people with lots of friends are more influential than people with only a few friends. Okay. So it's a reasonable centrality measure. It actually works pretty well. It's widely used in sociology, and it's extremely easy to compute. However, it's not perfect. And
Merkel has lots of friends.
Sorry?
So Merkel has lots of friends.
Okay. Maybe. So one thing that's arguably wrong with this measure of influence is that it basically just gives you 1 point for everybody you know. And in other words, everybody you know is sort of equal. Right? Well, obviously, this is not true in the real world. Some of your friends are themselves more influential than other friends. For instance, I might only have one friend in the world, but if it was the President of the United States, then I could be a pretty important person because I know the President of the United States, right? So it matters who you know, not just how many people you know. And that leads to the idea of eigenvector centrality, first proposed by Phil Bonasech, which says you get a number of points in proportion to how many points your friends have. So I just add up the scores of my friends. So my score, I'm node I, my score x sub I is proportional to the sum over the neighborhood of I of the scores of the people in that neighborhood. Or I can write that as just the sum over all nodes, adjacency matrix element times x sub j. In other words, in matrix notation, x is an eigenvector of the adjacency matrix. So x here is the vector of all the centrality scores. Which eigenvector should it be? Well, if you want all the scores to be positive, then it has to be the leading one, because Perron-Frouini's theorem says that that is the only one that has all elements positive. So this is the classic eigenvector centrality, the leading eigenvector of the adjacency matrix, widely used in many fields, and it's the basis, for instance, for the PageRank algorithm that Google uses to do its web search. So you can make money doing this. Here's another example, percolation, which many people have talked about. You can do percolation on a network, either bond percolation or site percolation. It's widely used, for instance, as a model of resilience of networks. You can think about removing the nodes or removing the edges from a network and then asking what's left. What's left is a percolation cluster on a network. And so, for instance, it's known that for sufficiently dense networks, the percolation threshold, the critical percolation probability for edge percolation on network, is just the reciprocal of the leading eigenvalue of the adjacency matrix. So both the leading eigenvalue and the leading eigenvector have simple physical interpretations and are therefore interesting things to look at. And there are many other examples as well, of course. So now let me ask the following question. Suppose I wanted to calculate the leading eigenvector of the adjacency matrix. How would I go about doing that? Well, there's lots of ways I could do it, but here's a very simple one. Let me just take any random starting vector and repeatedly multiply it by the matrix A. The so-called power method just means that the component of the starting vector that's in the direction of the leading eigenvector gets multiplied by the biggest number, and so if you do it repeatedly, eventually everything else dies away by comparison, and I'm just left with something which, to a good approximation, points in the direction of the leading eigenvector. So this is the standard power method. How fast does it work? Well, that depends on how fast the subdominant contributions die away. In other words, how large the subdominant eigenvalues are compared to the leading eigenvalue. If I have the leading eigenvalue and I have the next one that's pretty close to it, then it's going to take a lot of multiplications to get rid of the slowest, the second mode there, the slowest decaying mode. And if I let the eigenvalues get closer and closer together and eventually cross, then the running time of this algorithm diverges. This is very reminiscent of something that we're very familiar with in physical phase transition, so-called critical slowing down. The dynamical processes like this one have a time scale which diverges as you go through a phase transition. And in fact, you know, it's essentially the arguments you use to justify that in physics are essentially exactly the same thing. It's repeatedly multiplying by some stochastic matrix that gives you transitions between states, and it's precisely when the eigenvalues cross over that you get critical slowing down. So in a sense, this is exactly the same phenomenon. I'm illustrating it here with a picture I took from one of Chris Moore's papers, where they were doing, looking at the so-called detectability threshold in community detection and using a particular algorithm that they came up with for doing this, a belief propagation algorithm, and they showed that the running time of their algorithm diverges precisely as you go through this phase transition. So there's sort of, in a hand-wavy way, there's a suggestion here that phase transitions are happening at points where levels cross in the adjacency matrix. So what I want to do in this short talk is show you a couple of different examples where we sort of understand explicitly how that happens, of particular phase transitions, and then end with some speculation. So here's one example of this kind of thing. It's a so-called localization transition, and it involves the eigenvector centrality. So the eigenvector centrality, again, is the leading eigenvector of the adjacency matrix, widely used as a centrality measure. And typically, it will assign, you know, some varying centralities all over the network. But under certain pathological conditions, it can fail. And the failure mode is that all of the eigenvector centralities condenses onto one node, or sometimes a small number of nodes, and everybody else gets left out of the picture, and at that point it's no longer a useful centrality measure. So here's a simple model to understand how that failure mode arises. So what I'm going to do is I'm just going to start off with a standard random graph with mean degree c, so it's just a GNP type graph with p equals c upon n, where c is some number that I choose. And I'm going to start off by just calculating the eigenvalue spectrum of that matrix. Well, that matrix is just a random symmetric matrix with IID elements in it, and therefore its spectrum obeys the semicircle law. It's just a Wigner matrix. It's the standard simplest result in the first chapter of the random matrix textbook, which says that matrix should have a spectrum that follows the semicircle law, except not quite. That's not exactly right because it's not a centered matrix, right? The Wigner's theorem only applies for matrices where the random elements are centered on 0. They have mean 0, and they don't in the case of the adjacency matrix. They're off-center, and it turns out that shifting it off-center in that way, basically it leaves all of the spectrum untouched except that it generates one outlying eigenvalue. So here's the first example of the thing that I was talking about. You can show that the spectrum of this random graph is it has a semicircle like that with bounds that are plus and minus 2 square root of c, and it has one outlying eigenvalue there, which is value c plus 1. Why 1? Well, because there's only really one parameter in this model. I'm claiming that these outliers telling you about all the structure, and the band is telling you about all the randomness. So the structure in the random graph is just one parameter. If I've told you the average degree, in other words, if I told you this eigenvalue here, then I've told you everything. Everything else is just random fluctuation about that average degree, and all that random fluctuation is pushed into the band of continuous eigenvalues here. In fact, you can show that the eigenvectors in this band are just isotropic, hard-distributed unit vectors that just point randomly in any direction. So there really is nothing to see there. It's just random stuff in there. So all of the interest has been separated off into the high-lying eigenvalues. OK, so that's just a standard random graph. So now what I'm going to do is I'm going to take my random graph, and I'm going to add one node to it, a hub node. So I'm adding this node over here. So this is going to be my perturbation of the system. And I'm going to claim that this is what's going to give rise to the localization transition, adding this one hub node. So it's well known in the real world that many networks have a small number of nodes with very high degree. So it's not an unrealistic situation to consider what happens if I have hubs in networks with very high degree. So I'm adding this one extra node here, which is going to be randomly connected to all of the other nodes with some probability q, which is equal to d upon n. So in other words, d will be the expected degree of the hub node, and it's just randomly connected to everything else. So I can make d large, make this hub have very high degree, and that's what will drive us through this localization transition. So it turns out it's not difficult to work out what effect this has on the spectrum of the graph. This is the only calculation that I'll go through in any detail. It's really just to show you how simple it is. The adjacency matrix of this model looks like, so x here is the adjacency matrix of the original unperturbed graph, just the random graph. So that's an n-1 by n-1 matrix. And then I've added an nth row and column which represent the hub in the network. So this vector A just has ones representing which other nodes it's connected to. And I'm going to solve the eigenvalue equation for I'm interested in the eigenvalue z. So I'm going to solve this equation, and I'm going to write my eigenvector v in this form, the first n-1 elements and then the last element separately. And so I'm just going to substitute these forms into that equation, multiply it out, and I get these two equations here. And then I'm just going to eliminate v between those two equations, and I get this equation at the bottom here. So just straightforward algebra. So solutions of this equation for z give you the eigenvalues of this slightly more complicated adjacency matrix. Notice that it contains the so-called resolvent matrix in the middle, z minus x inverse there. What I'm going to do is I'm going to write that in its diagonal representation, z minus x inverse. So here, chi sub I is the ith eigenvalue of x, and little x sub I is the corresponding eigenvector. So I'm just writing it in its diagonal representation, substitute it back into the equation, and I get this expression here. This is the thing that I need to solve for the eigenvalues z. And then you look at this, notice that I've broken out the highest lying eigenvalue here. I know that the highest one is C plus 1, so I've just written that one explicitly. I don't know what these other ones are, so I just put them in there like that. And now you notice that this thing here has a divergence everywhere that Z passes through one of the eigenvalues of the unperturbed matrix, these chi sub i's. In other words, the left-hand side of the equation must look something like the blue curve in this picture. So the vertical dashed lines represent the unperturbed eigenvalues of the original random matrix just all on its own, that semicircle thing. Right, so here's the band and here's the one outlier. And the blue curve, the left-hand side of this, it has divergences every time you meet one of those eigenvalues. So it has to look something like this. It's got all of these divergences in it at the dotted lines. And then one more divergence out here at C plus 1. And then in the limit of large Z, it goes like 1 upon Z. And then the right-hand side is just that gray diagonal line across there. It's just Z. And where the two cross, where the blue crosses the gray, those dots are the things that I want. Those are the perturbed eigenvalues that I get by adding that one hub. So you can see geometrically what the structure is. First of all, we have an interleaving condition. This tells you that the eigenvalues of the new matrix lie in between the eigenvalues of the old matrix, so that if I let the graph become large and those eigenvalues get closer and closer together, you can see that the distribution of the perturbed eigenvalues is going to be the same as the distribution of the ones that I started with. In other words, it's going to be a semicircle again, except for this one out here, which is just at C plus 1, as it always was, and a new one that has appeared here in the middle of the gap before the old outlier. So this is the one that I'm going to be interested in. It turns out you can calculate what that is just by solving that equation that I wrote down, and its value is d upon square root of d minus c. Okay? So now my spectrum has got a bit more complicated. It's still a semicircle, and it's still C plus 1, but I've got this extra eigenvalue there. I've got two outlying eigenvalues, basically saying I have two parameters in my model, C and D. So spectrum got a bit more complicated. Okay, so now here's the thing. I'm claiming that interesting phase transitions happen when eigenvalues cross over. So I can make that eigenvalue there move by changing the degree of the hub. Just make D bigger, it will go up, and eventually I can make it cross over that leading eigenvalue there. When I do, that's where this localization transition happens. Solve for the position where that happens. It happens basically at D is about equal to the square of the average degree in the network. And what happens at that point is, well, I'll show you a picture. This is what the eigenvector centrality looks like before you reach that transition. This is what it looks like afterwards. What happens at that point is that a non-vanishing fraction of all of the eigenvector centrality concentrates on just that one node, the hub node. And you can actually calculate what fraction that is. It's given by this expression here. So there's sharp behavior at exactly the point where these two eigenvalues cross over, at which this eigenvector centrality fails because it just puts all of the weight on this central node and basically everybody else gets nothing. Yes?
Under the interleaving condition, it looks like you're suddenly
when you're
one of the eigenvalues is at C plus 1,
right?
So the other eigenvalue doesn't ever meet that one because it has to have the previous eigenvalue between them, right?
Oh, well, fair enough, actually. So if you look very carefully, it's not that the two cross over. What happens is this one comes along like this and stops, and that one moves off. They never actually quite touch. And this is well known in quantum systems as well. You don't actually have energy levels crossing over. They repel. That's what the physicists say.
There's no point at which they're actually equal to each other.
Technically, that's correct. They come order 1 upon n close together, but they never actually touch. So fair enough. So it's not truly a divergence. It's something of size n. In the limit of large n, that becomes as big as you like. Yeah. So this is sort of a failure mode of this particular centrality measure, and one that actually happens in real life. So a well-known example of this is what happens in power law networks of the power law degree distribution. They can have nodes large enough to trigger this problem, and means that standard eigenvector centrality actually does not work well on those networks at all. Okay, so that's one example of a transition happening where two eigenvalues cross over. Here's another example. I'm going to look at something that many people here have studied, groups or communities in a network. And the model I'm going to use to represent this is the most standard one, the stochastic block model. So I'm going to take a network where the nodes are divided into groups, and then I place edges within and between groups with different probabilities. I'm going to have just two probabilities in this case, P in and P out, for edges within groups and edges between groups. And if P in is much bigger than P out, then you get sort of traditional community structure, i.e. dense clumps of nodes connected together by only sparse edges between them. So this is a very simple model for the kind of clumpiness that one often sees in real-world networks. And now I'm going to ask, what is the spectrum of this? I'm not going to do the calculation for you, but it's, again, very straightforward random matrix theory, the kind you'll find in a random matrix theory textbook. And again, what you end up with is a semicircular band and an outlier at t+1, plus an additional eigenvalue here in the middle of the band, which takes this slightly complicated value, where C in and C out are just rescaled versions of the probabilities P in and P out for the edges. So now, again, in this case, I can move this eigenvalue around and cause phase transitions to happen as it meets other eigenvalues. So this eigenvalue here in the band is now the one that is telling you that there's community structure in your network. Right? If it wasn't there, the spectrum would just look like an ordinary random graph. The reason I know it's not is because I see there's this extra outlier here. So again, sort of the information in the model is there's sort of really two parameters, P in and P out, and therefore I have these two outlying eigenvalues that are telling me all the structural information in the network. And moreover, as is of course well known, the eigenvector corresponding to this eigenvalue can tell me about the details of that community structure. If you look at it, here's an actual numerical calculation for a small network with 1,000 nodes. If you look at it, you see this was a network with two groups in, and you can see the two groups very clearly in the eigenvector. It was the first to have 500 nodes and the second 500. And you can see that these ones mostly have positive eigenvector elements. These ones mostly have negative eigenvector elements. So if I simply split the nodes according to the signs of their eigenvector elements, then I assign most nodes to the correct group. So here was a simple example, generated a little network, and then I plotted the network by making the vertical position of each node equal to its eigenvector element in that second eigenvector. And what that does for you is it very nicely pulls out the two groups. Here's one of the groups I put in the network. Here's the other group I put in the network. This is an example of so-called spectral embedding, which is a class of visualization algorithms where you use the elements of the eigenvectors to decide where you're going to put the nodes in some space. I'll skip this. There's a fun example here of that, but I'll skip it since I only have a couple of minutes left. How many minutes do I have left? A little more than 5 minutes. Excellent. Okay, very good. Right. So this is a standard approach, of course, been well known for a long time, since the 70s, that if you look at the second eigenvector of the adjacency matrix, it tells you about partitions and community structure in networks. This is not a new idea, but what I want to ask about is phase transitions that could happen in this system when the eigenvalues cross over. So you could imagine one thing we could do is what we did in the previous example and push this eigenvalue up by changing the values of these parameters C in and C out to make it cross over this leading eigenvalue here. But that's actually not what I'm going to do this time. I'm going to push it down and make it cross over the edge of the band here. When it does that, when it disappears into the band, the spectrum will, for all intents and purposes, now just look like the spectrum of an ordinary random graph. It'll just be the semicircle and the C+1, and there'll be nothing else. So at that point, if you were only looking at the spectrum, you'd say, oh, it looks like I just have a random graph here. There's nothing going on. There's no community structure in this. So one might suspect that the point at which this happens is the point at which community structure disappears in the network. And indeed, it turns out that that's correct. What's a little surprising about it is you might think that the point at which the community structure in the network disappears is the point at which C in equals C out. So that the probability of connections within groups is the same as the probability of connections between groups, but it turns out that that's not the case. The remarkable thing is, it turns out that this transition happens at an earlier point where there's still a non-zero difference between C and C out. In other words, potentially you are putting community structure in the network, but it's not turning up in the spectrum. So you can calculate where that transition would happen just by setting 2 square root of C equal to that expression there and solving, and it turns out that it happens at the solution of this equation here, C in minus C out is square root of 2 C in plus C out. This, in fact, is a well-known transition, first pointed out by DeSalle and collaborators in this paper. So it's the so-called detectability threshold in networks. There is a well-known threshold as you make the community structure in the network weaker, below which it becomes impossible to detect that structure. So what you're seeing here is we're just finding that transition again, but by a different means, looking at places where levels cross over in the spectrum of the adjacency matrix. One of the nice things about this approach is that you can actually take it further. I said we were just going to divide the nodes into groups according to the signs of their eigenvector elements. One of the nice things is we can actually calculate what the eigenvector here is, or more specifically, we can show that within each group you have normally distributed eigenvector elements, and you can calculate the mean and the standard deviation of those normal distributions. So I have Gaussian up here, and I have Gaussian down here, and I know the mean and the standard deviation. And then I classify things according to the signs of the elements. That gets most of the guys up here right. They're in the positive half, and most of the guys down here right. They're in the negative half. But there are a few that you get wrong. Anywhere that the line crosses 0, the dotted line in the middle, you get it wrong. There are a few in group 1 here that actually have negative elements, and so will be classified into the wrong group. And a few over here that have positive elements, and so will be classified into the wrong group. And since I know the mean and variance, I can estimate in expectation how many of those wrongly classified vertices they're going to be. It's just some expression that depends on a Gaussian error function. So I can actually get a closed form expression for the rate at which this algorithm succeeds. And it looks like this for high values of C in C out minus C out. In other words, for very strong community structure in your network, you do very well, you classify most vertices correctly, but there's a phase transition. There is a sudden jump at which you fail. 0.5 here is the failure point. If you tossed a coin, you would get 50% of the nodes right. So if you're getting only 50%, you've completely failed. And you can see that there is a sharp transition. Each of these curves has a sort of L there. That's the phase transition I talk about. The points in this figure are just numerical results, just to check that everything's working. Okay, so there's two examples of well understood phase transitions that occur at points where levels cross over in the adjacency matrix. So as I say, this is not a new idea. This is well known in several other fields, in particular in quantum phase transitions. What I think is interesting about this in the context of networks is that there are many cases where we can find crossings of energy levels in networks of eigenvalues of the adjacency matrix, but we don't actually know what the corresponding transition, if any, is at that point. In other words, I can point to you to places in the parameter space of simple models of networks, and I can say, I believe there is an interesting structural phase transition that happens at exactly these parameter values, and I have no idea what it is. This is sort of fun because it's the opposite of the situation that we're usually in, at least in physics. Usually we know about a phase transition happening, but we don't understand it mathematically. We can't calculate where it happens or what its critical properties are. In this case, we can calculate all that stuff. We know where it's happening, but we just don't know what it is. Something interesting happens at this point in this model, but I don't know what it is. And I can give you examples of that if you like, but I guess I'm out of time. So, well, okay. So let me give you one very quick example here, which is from that localization example I gave you with the hub in the network. So I could, in that case, I had the band, and I had two outliers, and I looked at the transition that occurs when these two cross over. But in principle, there's another transition that occurs when this one here, is a d over square root of d minus c, crosses over the edge of the band, which is at 2 square root of c. So you can calculate where that transition happens. So in fact, it happens when d is equal to 2c, when the degree of the hub is twice the average degree in the network. And what would you think that was? Well, when this crosses over the edge of the band and disappears, what you're left with, again, is just the standard spectrum of the random graph. In other words, by sort of analogy with the community detection case, you might think that what's happening here is a sort of detectability threshold for the hub in the network. Below that point is the point at which you fail to be able to detect that you've added the hub to the network. It just looks like a random graph. That would be your guess, but it turns out that that's wrong. That's obviously wrong because the transition occurs at d equals 2c, which is easy to detect, right? If c is 100, then d equals 2c is 10 standard deviations away from the mean, and if you can't detect that, then you're doing a very bad job. So it's really easy, even after this eigenvalue disappears, it's really easy to detect the hub. So that's not what's happening. So what is happening? I don't know. But I suggest that there is some interesting structural phase transition that happens at that point. And you can come up with other examples as well. Anyway, I'm out of time, so let me just say thank you to my terrific collaborators. Travis and Thomas are 2 graduate students in my group, and Raj is a fellow faculty member at the University of Michigan. And thanks to you for listening, and that's it.
I didn't understand what your graph model was. So C is constant, n goes to infinity, and you're taking edge probability C over n?
C is constant, n goes to infinity. Right.
But then
You have to be, yeah.
you have isolated vertices, for example. So that
Yeah, so you have to be a little bit careful about this. So this is, it's never, so to be fair, it's never exactly correct, right? So this is sort of correct in the limit of large but constant C, but you never actually get there. So it is a rather delicate situation. You could probably imagine some sort of thing where you take n to infinity first and then you take c to infinity or something like that. But essentially, what you're thinking about is fixed c, and the approximation really gets better as c becomes large.
Why not take C in, C out, or whatever, one of these graphs?
Take c in, c out.
Or
Yeah,
just
the same
C
thing.
out,
The same thing.
or end of regular.
nothing is exact.
Yeah, as long as c is constant, it's
Yeah.
never going to be exact.
Yeah.
Equals
But
what?
the vector seems will be much better. There are no isolated vertices.
Oh, I see. Okay, fair point. Yes, indeed, you might be able to do that. Yes.
Is there an analogy with the planted clique model?
Yeah.
G and a half, and you can put in a.
Absolutely. So you can analyze the planted clique model in exactly this way, and actually this was done a long time ago, and it's well known that the phase transition in the detectability of the clique occurs exactly at the point where the corresponding eigenvalue hits the edge of the band. Yeah, and that's been known for quite a while. So indeed, I could easily have given that as another example. Yes.
But the interesting thing is that there are cases where the spectral algorithm isn't optimal and where there are other algorithms that get more information. So, I guess what's happening in your hub detection is that at that point the spectral algorithm fails, but as you pointed out, there are other algorithms, like in that case, looking at the degree, which are enough. Although I guess the interesting thing about these hubs is that if C really is constant, then of course by chance there are some things that large. So this also, I'm trying to think about it, this case also involves some sort of limit as C goes to infinity as some function, some slowly growing function of n.
Absolutely, it does. When I say that you can detect the hub at the level of 10 sigma, there's still some 10 sigma chance that you will fail. Right, absolutely. So yeah, for any finite C, it's not as sharp.
So like in the planted clique problem, there's one size which is detectable by standard spectral algorithms, but then people have succeeded in doing somewhat better than that. Trickier algorithms.
Yes, and of course, in principle, that's true in community detection as well. That at least in certain cases, below the transition, there's non-polynomial algorithms that could succeed better in chance.